Thank you so much for the introduction. I'm very happy to be part of this colloquium, this fantastic conference. I enjoyed many talks already of this week. And my talk is a contribution to the real singularity theory that combines real singularity theory with cobordism theory. And before I go into the details of what a cusp cobordism is, I would like to locate the topic in the broader context of differential topology. So let me assume throughout the talk that all manifolds and maps between manifolds are smooth, that is differentiable of class C infinity. And then it is a fundamental classification scheme in differential topology to consider smooth manifolds up to cobordism relations. And so the most classical examples are the cobordism groups of smooth manifolds, omega NO and omega NSO, corresponding to either unoriented or oriented manifolds, actually, of dimension n. And these are well understood. These have been studied classically throughout the 20th century. And one important contribution is due to René Thom in his seminal paper, Quelques propriétés globales des variétés différenciables from the mid-50s, where he was able to compute them at least rationally. I would like to point out that he applied the Pontryagin-Thom construction to associate to any cobordism class of such manifolds an element in a certain homotopy group by using an embedding of the manifold in a higher dimensional Euclidean space. And this is the perspective I would like to stress here. We can consider, therefore, the cobordism group omega NSO as a cobordism group not only of manifolds, but actually of embeddings of manifolds into Euclidean space of sufficiently high dimension. And once you have recognized this, you can go further and ask about cobordism theory for maps that are more general than embeddings, so smooth maps with singularities. And this kind of question has been approached through stable homotopy theory by many people, including Wells, Riemanni, Schütz, Sadikov, and Ando, who received quite general results in this context. Today, I would like to take another direction and consider in particular Morse functions, which are in some sense the most simple smooth maps with singularities. And rather than using complicated stable homotopy theory in an abstract way, I would like to benefit from geometric topological methods that are rather explicit, like elimination of cusps, for example, that we will see in the following. And now I would like to explain what is the cobordism relation for Morse functions in the most classical natural setting. So we are concerned now with Morse functions on oriented closed n manifolds M. Let me just recall that by a Morse function, we mean just a function such that for each singular point you find in a suitable chart that the function f looks like the standard quadratic form in n variables with a few minus signs possibly. And having now two Morse functions, f0 on a manifold m0 and f1 on a manifold m1, let me define the notion of an oriented cobordism between them. So such a cobordism is assumed to be a pair WF, like indicated in the picture, where W is an oriented cobordism from M0 to M1. So like in the picture, you see like a pair of pens indicated as W. On the left-hand side, you have the M0. On the right-hand side, you have the M1. And now the map F, capital F, is interesting. This is supposed to be a map of W into the plane, or the product of the unit interval with the reals. And this F is assumed to be a map such that if you restrict F to tubular neighborhoods of M0 in W or M1 in W, then F should look like the product of the identity on the interval for a small epsilon times either the Morse function F0 on the left side or the Morse function F1 on the right side. And in between, F is assumed to be a fold map. So if you restrict F to the complement of W minus its boundary, M0 union M1, then you assume that F is a fold map in the following sense. Every singular point of this restriction is assumed to have the following normal form. So you have n+1 coordinates, x0 to xn, and you want to map this to the pair where the first component is given by the projection just to the first component, x0, and the second component is given by the standard quadratic form in n variables in the remaining n coordinates, x1 to xn. And so you see the normal form of a fold map is just the suspension of the normal form for a Morse singularity. In this sense, it is very natural to call this pair WF an oriented cobordism from the Morse function F0 to the Morse function F1. And well, when you think about it, you can define cobordism groups now using this cobordism relation. So there are two flavors, either the unoriented version, which arises by forgetting about orientation in this definition, and also the oriented cobordism group of Morse functions, which I will write Fn instead of FnSO in the following. These are groups by means of disjoint union. So you take disjoint union of manifolds and also the disjoint union of the Morse functions on the manifolds. And you can add elements by taking these disjoint unions. You can also take the negative of an element by multiplying the Morse functions by -1, and if the manifold is oriented, by reversing the orientation. And the identity element is represented by the empty Morse function on the empty set, which is also a manifold of dimension n in this sense. So using these groups, these abelian groups, there were early results due to Ikegami, Saeki, and also due to Kalmar that clarified the structure of these groups in the case of Morse functions on surfaces. So the case of Morse functions on an oriented closed surface is solved to be Z, and the unoriented case turns out to be Z plus Z2. The whole picture has been clarified by a theorem due to Ikegami in 2004, where he computes all cobordism groups in every dimension, even in higher dimensions, both in the unoriented and in the oriented case. And it turns out, as a direct summand, in both cases, you get the cobordism groups that I mentioned earlier before. And then you get some direct Z summands that come from certain properties of the Morse functions that live on the manifolds. And in the case that you take the oriented cobordism group, there is also an additional summand Jn, which is either torsion Z mod 2, or if n is equivalent to 1 mod 4, or else it is just 0. So this is the structure of these cobordism groups in all dimensions. This is the whole picture. So now we are basically done with the whole theory, but you can as well consider Morse functions in various different flavors. So for example, you can introduce index constraints on Morse functions. This is what Saeki did. He in particular considered Morse functions that have only maxima and minima as their critical points. So only critical points of maximal, of extremal indices. And then it turns out the cobordism groups that arise, if you also adapt the notion of fold maps that are allowed, the fold indices, then Saeki has shown that the cobordism groups you get are essentially isomorphic to groups of homotopy spheres, which means that in particular, the cobordism theory of Morse functions, or in general smooth functions under index constraints, are strongly related to differentiable structures on manifolds. Another instance of this principle is also another paper of mine on bordism of constraint Morse functions, which generalizes Saeki's results, but I will not go into detail on this topic today. There are other flavors you can consider for Morse functions. For example, circle-valued Morse maps. So instead of mapping into the real line, you map into the circle. And then it turns out, due to a work of Ikegami and Saeki, such cobordism groups have applications to map germs, and they were able to construct topological invariants of certain map germs by using this theory. And the viewpoint I would like to take today is Morse functions on compact manifolds with boundary, or possibly with boundary. So far we have considered Morse functions on closed manifolds. And now in 2016, Saeki and Yamamoto suggested to study cobordism theory of Morse functions on manifolds, possibly with a boundary. And there are several contributions. And I would like to focus on a paper of mine today, Cusp cobordism group of Morse functions, which has recently been accepted for publication in the Journal of Topology and Analysis, and the preprint is still available on arXiv though. And I would like to explain in more detail what this theory is about. So let me consider now manifolds possibly with boundary and Morse functions on them. So suppose that M is a compact n-dimensional manifold, possibly with boundary, and the dimension of M is supposed to be at least 2, which is important because the boundary will have dimension at least 1. This is important for the following definition now. We say a Morse function on M is a function f on M, which is assumed to be a submersion in the neighborhood of the boundary, so no critical points of f are there, but we assume in addition that the critical points of both f and its restriction to the boundary of M are all non-degenerate. So in particular, if you restrict a Morse function of a manifold possibly with boundary to the boundary, then you get a Morse function on the boundary in the sense we had before by this definition, because all critical points on the boundary of the restriction of f to the boundary are non-degenerate. And now, to be more concrete, I would like to give some low-dimensional examples here. So these pictures show Morse functions on certain surfaces that are embedded in the Euclidean 3 space. And the Morse functions are induced here by height functions, so you can really look at them. On the left-hand side, you see the manifold M taken to be the 2 torus with a little 2-disk, with the interior of a little 2-disk removed. And the embedding is as indicated in the picture. So the black dots indicate critical points of F1 in the interior of the manifold M, and the blue dots indicate critical points of the restriction of F to the boundary of M. And as you can see, there are no critical points of, no black dots on the boundary, so no critical points of F1 on the boundary, but only of the restriction of F1 to the boundary. So this is clearly a map that satisfies our assumptions. So this is a Morse function. On the left-hand, on the right-hand side, you see another manifold, just a 2-disk embedded like a cap. And you see there is one interior critical point, the black dot, and there are 2 boundary critical points, the blue dots. And again, this is a Morse function on the surface M. Okay, so now let me introduce what the cusp cobordism of such Morse functions is. So now we have, as before, we have to define what an oriented cusp cobordism from a Morse function f0 to a Morse function f1 is. And this time it is a triple WVF, where the pair WV is assumed to be an oriented cobordism that is allowed to have corners and goes from M0 to M1. M0 and M1, recall, these are manifolds possibly with boundaries, so it is natural to assume that the cobordism now has possibly corners. And the corners should be along the boundary of V, which is also the union of the boundary of M0, which with the boundary of M1. Let me just indicate this by a little picture. So you can schematically think of W as a rectangle here. And V is now these boundary parts. And then we have M0 on one side and M1 on the other side. So the whole boundary of W decomposes into parts, namely V and the union of M0, the disjoint union of M0 and M1. And the corners of W are along the boundary of V, which equals the boundary of M0 unified with the boundary of M1. So this is the picture you should have in mind at this point. Okay, so the pair WV is a cobordism possibly with corners like this. And the map capital F is a map again into the plane with the following properties. I will make a picture in a moment. So first of all, we assume again that the behavior near the boundary parts M0 and M1 is again like a product. So on the left-hand side, you find a color neighborhood where F restricts to a map that looks like the product of the identity times F0, the Morse functions on the left-hand side. And on the right-hand side, similarly, we have the product of the identity map on a suitable interval times F1. Then, secondly, the restriction of F to the interior of W, so W without all the boundary, is a generic map. So since F maps into the plane, we have two possible singularity types, namely fold points, and also cusp points are allowed here. That's why we call it a cusp cobordism. In contrast to the cobordism I introduced in the beginning, the notion of a cobordism for Morse functions, which did not allow cusps, because then you would have a generic extension, which is always possible. But here it is okay to assume cusps because we will still measure some non-trivial cobordism invariants. And also, now this is the most complicated condition here. We assume that the map germ of F at every point X in V minus the boundary of V, so on these parts of the boundary that are not M0 and M1, these are boundary points, and there we assume that capital F is right-left equivalent to one of the following regular C-infinity stable map germs at the origin of the upper hyper space in Rn+1, so Rn times the closed interval 1 to infinity. And we have three different types that are all pairwise non-equivalent. So we have n+1 coordinates, x0 to xn, and the first type is a so-called boundary regular point. So we just project to the first two components. And this is obviously also a regular point of capital F, but the restriction to the boundary, so to V, will also be a regular point. So that's why we call it a boundary regular point. The next type of singularity is we map the tuple x0 to xn to the pair x0, comma, and now here's the normal form of a Morse function again, plus xn. So adding xn here also makes this normal form a regular form of F, but the restriction to the boundary, which amounts to setting xn to 0, is obviously a fold map. So this is not a regular point of the restriction to the boundary. And hence it's not equivalent to the first normal form. And also we have the third one, which we call a boundary cusp, which is more complicated, but essentially this is a regular point of capital F such that the restriction of capital F to V, to the boundary part of W, is a cusp on the boundary. So the restricted map has a cusp point there. And if we allow these types of local normal forms, then we call the triple WVF an oriented cusp cobordism. So now let me give you a more elaborate picture of such a cobordism. So here again, we see the cobordism W like as a pair of pants, but now we have the boundary part V, which is marked in blue here, which makes holes into this pair of pants somehow. And then let me just check again the assumptions we made on capital F as a map into the plane. So first of all, the behavior near the boundary parts M0 and M1 is a product behavior as before. And then the restriction to the interior of W is supposed to be a generic map. So I indicated this by using these red lines in the interior of W, which indicate fold lines. And you see at some point here are cusps here and there. These are cusps indicated also in the plane. So this is a generic map, the restriction to the interior of W. And on the other hand, the map germ of f at every point on the boundary part V, which is the blue part, is assumed to be now one of the following regular C infinity stable map germs that I mentioned before. Due to low dimensional confusion, I cannot indicate this in the picture, but one thing I can say, the picture actually does not show a cusp cobordism for the following reason, because in the picture, you see that the fold lines from the interior of W run into the boundary V in these 2 points that I mark in green here. And this is not allowed because now the restriction of capital F to these points is actually, the behavior of capital F near these points is actually a singular behavior. So it is not one of these regular C infinity stable map germs. So this is actually, I should note this here, not a cusp cobordism for this reason. But there are many examples of cusp cobordisms as well, and we assume now for our cobordism relation that we have a cusp cobordism. So now, as before, this cobordism notion gives rise to cobordism groups that we call now cusp cobordism groups of Morse functions. So there are again 2 flavors. One is the unoriented version, if you forget about all orientations, and the second one is the oriented version. And again, the question arises, how do these groups look like? And now there is a result of Saeki Yamamoto, who introduced the notion of cusp cobordism in 2016. And they showed, first of all, that these groups are still interesting. So they are not completely zero, which might be the case because we used also generic maps. But there is, in fact, some non-zero information going on. And they introduced actually a notion of admissible cobordism, which is a bit more complicated than the definition I gave, because they also assume stability of the maps. So fold maps are only allowed, fold lines are only allowed to cross normally in the plane, and cusps are not allowed to coincide with other fold lines and cusps. But this can be eliminated. So these notions are basically the same, so I don't go into detail here. Then later, their result was based on an application of computing the certain cohomology groups of a universal complex associated with singular fibers, so quite an abstract approach. And later they were even able to improve their result. They showed that the unoriented cusp cobordism group of Morse functions on surfaces again is isomorphic to Z mod 2. And they published their result in the proceedings of the 8th International Workshop on Real and Complex Singularities at the University of Sao Paulo. So this was in 2016, and they used combinatorial arguments here based on labeled REAP graphs. So since they map into the plane and the cobordisms are 3-dimensional, if you consider 2-dimensional manifolds on the boundaries, then the fibers turn out to be 1-dimensional. So these can be considered as graphs. And then they use certain label arguments and combinatorial arguments and classification theory to compute this cobordism group. But the problem is, unfortunately, that these arguments are limited to the dimension 2. So they do not generalize to higher dimensions. And this is why they posed as an open problem in their paper to compute these cobordism groups, both unoriented and oriented, in higher dimensions. So for Morse functions on manifolds of dimension at least 3. And this is what I will present now. I was able to compute these cobordism groups with a different approach. So I used explicit geometric topological methods of global singularity theory to understand these cobordism groups. So let me present now the main result of this work. So first of all, I have to talk about the curly sign of boundary critical points of Morse functions. So again, let me say we want to compute as a goal the cobordism groups, the cusp cobordism groups of Morse functions by methods of global singularity theory. And the idea here is to not only consider critical point data, like in the pictures I drew, but also we want to include the information of how a Morse function f extends to a non-singular boundary map germ. Remember, the definition of Morse functions was such that near the boundary of M, we did not allow f to have singular points. So we have a non-singular extension of a Morse function on the boundary here, and we want to include this data in a clever way. And there's a paper of Curly from the 70s, where he assigns to every critical point of the restriction of a Morse function to the boundary a sign, which can be plus or minus. And the sign is defined in such a way that if you take the differential at this critical point of the boundary, on the boundary, and take an inward pointing tangent vector, then you want to point into the positive r direction if you multiply by this sign. So let me go back to the examples that I gave before for Morse functions on manifolds, possibly with boundary. So on the left-hand side, we identified two critical points of the restriction of F1 to the boundary. But since the map F1 itself is non-singular at these points, the arrows that point to the inward at the boundary points, that point to the inward of the manifold M, these arrows will be mapped to non-zero arrows in the real line. And now you see what the signs are. For the upper singular point of F1 restricted to the boundary, the down pointing arrow points down in the real axis, and thus the curly sign will be minus. And for the lower critical point, an inward pointing tangent vector at the boundary point where the map F1, where the restriction of F1 to the boundary is a singular point, this arrow will be mapped to an arrow pointing to the positive direction of the real axis. So there is a plus as the curly sign. So here we have one minus and one plus curly sign. For the second example, where the manifold M is a two-disk, we see that analogously that both inward pointing tangent vectors are mapped to non-zero vectors that point into the positive real direction. So here we have positive curly signs. So, and this way you can in general declare a curly sign. So Curly did this in the 70s to study non-singular extensions of Morse functions of oriented surfaces to compact three-dimensional oriented manifolds. So he also studied an extension problem, and in a setting where the manifolds are, where the cobordisms are three-dimensional. And we use this curly sign now in any dimension. Okay, so this is one ingredient we need to state the main result. And then now I would like to present the main result itself. I need some more notation here. First of all, for a Morse function on a closed n-1 dimensional manifold, let's say G, we denote by a new I of G the number of critical points of G of index I. So where the normal form of the Morse indices of the Morse critical points have I minus signs in the quadratic form. And the number of these critical points is denoted by nu I of G. Next, I would like to remind you of an Euler characteristic formula from Morse theory. So the Euler characteristic of P can be computed by taking the alternating sum of the numbers nu I of G. This is a classically known fact. But now we work not with Morse functions on closed manifolds, but with Morse functions on manifolds with a boundary. And now the Morse function is defined on a compact n-dimensional manifold, possibly with boundary n. And then I want to give a modified definition of this nu I. So I define something I call nu I plus of F. And this number is the number of critical points of the restriction of F to the boundary, which is again a Morse function on a closed n-1 dimensional manifold like the G before. But now we do not only count the number of those critical points that have index I, but also we want the curly sign to be +1. So we incorporate also data that come from the map little f, not just from its restriction to the boundary. And actually it depends only on the boundary germ of little f. So that's why I write here brackets f instead of round brackets. So this number is important in the following. And then we also take a modified Euler characteristic formula. So we call key plus of f to be the alternating sum over these nu I plus of f, in analogy to the Euler characteristic formula I mentioned before. And having this at hand, we can now state the main result, which is as follows. So for any dimension n, at least 2, we have an assignment that assigns to a Morse function f on a manifold M of dimension n, possibly with boundary and compact. It assigns the difference in the integers of the Euler characteristic of M and this modified Euler characteristic of f. And this difference turns out to induce group isomorphism, both of the unoriented and the oriented Cusp cobordism groups in any dimension n between the group and either z mod 2 in the case that n is even, or the integers z if n is odd. And this is the answer. And note that in particular, the two flavors of the cobordism group, the oriented and the unoriented, are both isomorphic in this case, which was not the case in Ikegami's result, but he had a different cobordism notion. So there's a different approach. But here I would like to present now some details of proof, of course, not too much in view of the time, but I will at least give you an idea of what happens in this proof. So first of all, I would only like to discuss the even dimensional situation. So we assume now n is even. And then I would like to reduce the claim of the theorem here to a theorem A, which says that if n is even and f is a Morse function on a compact n manifold, possibly with boundary, then the following statements are equivalent. So the first statement says that there is a Cusp cobordism, WEF, as we defined it before, from the Morse function f to the empty Morse function. So the Morse function on the empty n-dimensional manifold, on the empty set. And in other words, we say here that the Morse function f is null cobordant in the sense of Cusp cobordism. And the second claim is purely like algebraic in terms of algebraic invariance of the Morse function f. Namely, the second statement is that the Euler characteristic of M is congruent to the chi plus of f mod 2, where chi plus of f was the modified Euler characteristic of the Morse function f. So let me just explain how this theorem A implies the main result when n is even. So first of all, we are interested in this assignment from the cobordism, from the Cusp cobordism group into Z mod 2, given by sending the cobordism class of the Morse function to this difference, as I explained it. And first of all, this is now well defined because by implication 1 to 2 of theorem A, if you have a null bordism, then the two numbers that you subtract from each other are congruent mod 2. So this is in fact well defined by the implication 1 implies 2 of theorem A. And conversely, if you use the implication 2 implies 1 of theorem A, then you see that this assignment is also injective because if something is mapped to 0 mod 2, then the two numbers are congruent mod 2, as in claim 2 of theorem 1, and then you get a null cobordism, a Cusp cobordism from f to the 0 z, to the Morse function on the 0 set. So then you see this map is also injective. So to show that it is bijective, which is not so much, there's not so much to do anymore because you map into Z mod 2, so you just have to show it's surjective. You just have to find a non-trivial image, an element in the image that is non-trivial. So you just construct a concrete Morse function on the n disk, such that all critical points of the restriction to the boundary have negative curly sign. And then you see that the Euler characteristic of the n disk is 1 because it's contractible. And the modified Euler characteristic of this Morse function is 0 because all curly signs are negative, so they are not counted. We only count the critical points of the restriction to the boundary with positive curly sign. So here in this case, you get 1, and 1 is congruent, not congruent to 0 mod 2. So here you have, in fact, a non-trivial element in the image. And then you see that this is, in fact, an isomorphism. But the interesting part is, of course, to see why theorem A holds. And now I do two more reductions of theorem A, which are not so much in detail, I guess. due to the time, but I will at least explain the ideas. So keep in mind again theorem A. We want to characterize null cusp cobordisms in terms of these invariants. And the idea behind proving theorem A is now that the two statements of theorem A depend only on the non-singular boundary M germ H of the Morse function f. What does this mean? So what does this mean for statement 1? In statement 1, we said we want that there's a cusp cobordism from f to the empty Morse function. So, and such a cusp cobordism, capital F, turns out to be a generic extension of its non-singular V germ. So remember again, F is defined on the cobordism W, possibly with corners. And this picture here on the left shows you such a picture where now the right part of the rectangle has been removed because you get a cobordism from M to the empty set. So I rather draw a semi-disk. And on the left side, on the left-hand side, you have a boundary part M, and then you have another boundary part V. And now what you actually want is a cusp cobordism capital F on all of W, but what you actually need only is the restriction of F to a tubular neighborhood of V in W, because the rest can be extended generically, because we assumed in the interior of W, capital F is allowed to have also cusps, not only fold points, so we can choose a generic extension. So here we only are actually interested in constructing such a capital H, which is the restriction here of capital F to this tubular neighborhood of V in W. And secondly, for statement 2, this Euler characteristic chi plus of F depends actually only on the boundary germ H of the Morse function F, as I mentioned before. And also now this is important. Now we use that n is even. If you have the Euler characteristic of M, and you also have a second compact n manifold M prime. Here's a prime missing. Such that the boundary of M prime is the same as the boundary of M, then the Euler characteristics agree mod 2. This is a consequence because we work in even dimensions here. And so you do not really need the manifold M either, because you could take any manifold M prime that is bounded by the boundary of M. So we actually need only the information near the boundary of M. And so therefore we can reduce theorem A to theorem B, which is a bit more technical here. I will just mention it quickly here. So we again have the equivalence of two statements, but now we only have the manifold V, which is a connected compact N manifold, possibly with boundary. I would have to say also why we can assume connected here, but this is not so important now. And now we take H to be a non-singular function in this product, boundary V times half interval 0 to infinity. So this is like the restriction of the Morse function near the boundary. That's the non-singular function. And we also assume that H restricts to a Morse function on the boundary of V. And then the following statements are equivalent. First of all, there's a non-singular map capital H. This is now morally, this is now the restriction of the map capital F. That's all that remains here. That has a nice behavior that should be in some color neighborhood, should have the behavior again as a product of the identity with H. And also it should be generic if you restrict it to the boundary, to the boundary of this tube here, which is V times 0. And also the second statement is now that we have this algebraic congruence, which is now a bit more abstract again. And now there is one more reduction step, how to prove theorem B. Actually, we want to be more abstract. We want to work with an abstract curly sign here in the proof. And so we assume that we have only a Morse function on the boundary of V. Before we had, see in this theorem B, we had a non-singular function H already that restricts to a Morse function on the boundary of V. But now we only want the Morse function on the boundary of V. And all that remains from this non-singular extension is just an abstract curly sign that is assigned to the critical points of this restriction to the boundary of V. And in these terms, we can show that I just say this here, I cannot explain it, that the restriction of H in the theorem B of the map capital H, the restriction to V times 0 extends to the non-singular map H if and only if each component S of the singular locus of G that contains an odd number of cusps of G has endpoints such that the abstract curly sign coincides. And I wanted to indicate this in this picture here, in this left picture. I make it a bit bigger. I hope you can see it. So the curly signs come from these inward pointing vectors on the boundary. And now, roughly speaking, since we consider cobordisms of these Morse functions on manifolds, possibly with boundary, these curly sign inward pointing blue arrows also extend along the fold lines. And each time you run through a cusp, this happens. These arrows, they change the side. So if you run through a cusp, then the blue arrow, like in the picture on the right here, the blue arrow will turn into the red arrow. And before you reach the cusp, you point into the right-hand side of the fold line. And then after running through the cusp, you point to the left-hand side of the fold line. So there is a change of orientation going on. And this is captured here by saying that if you have a component S of the singular locus of G that contains an odd number of cusps, then you want that the endpoints satisfy that the abstract curly signs agree. Only then you will be able to construct a non-singular extension. And the second statement of theorem B is just saying that you can replace the generalized Euler characteristic formula by using the abstract curly sign. So what we end up with is a theorem C, and here you only work with an abstract curly sign, and here you will see that these two statements should be equivalent. Again, some algebraic congruence and some existence of a map capital G, which is now only defined on V. So not even in a neighborhood of V in W, only on V. And here you want it to be generic inside the interior of V. And you want this condition that every component which contains an odd number of cusps of the singular set of G has endpoints where the curly sign agrees. And now, to prove the theorem C, I will just indicate here that you actually, to construct the map G, you are actually interested in the last property about the parity of the cusps on the singular components of G. And here you need to prove the implication that 2 implies 1, you need to use Levin's cusp elimination technique, as well as the complementary process of creating pairs of cusps along fold lines to be able to manipulate the singular set of such a candidate capital G to achieve that the formula 0.1, which is here a certain formula, that this holds for every component S when it holds for the sum over all S, as we wrote it here. So you need to modify the combinatorics of the number of cusps lying on the fold lines to be odd. And to do this, you have to manipulate this. And this is only in the case that n is even. So the case that n is odd would have a different argument of the same flavor, but I wanted to focus on only this here. So now let me come to the end. I just want to say that there are also other variants of notion of cobordism of Morse functions for Morse functions on compact manifolds, possibly with boundary. For example, you can say there should be no cusps and no boundary cusps allowed for the cobordisms. Or another variant is if you allow no cusps, no boundary cusps, and no B2 points. These are the points I mentioned before in the picture that made our cusp cobordism not be a cusp cobordism in the picture. So these could be allowed, and this leads to a different notion of cobordism with different properties. And these have been studied by Yamamoto recently. This was published in the case, again, of Morse functions on surfaces. And in upcoming work, I will also be able to generalize these computations to general dimensions with different arguments, though. These are not so easy to generalize to other cases, to other notions of cobordisms. And then there is also the idea to study cobordism relations for Morse functions on compact manifolds with corners, where you might get more interesting or a bigger variety of local normal forms to consider for defining the cobordism relations. Okay, let me stop here. Thank you very much for your attention.